Hello students, today we're going to talk about Chapter 12, Tectonics, Earthquakes, and Volcanism. Now rocks are subjected to stress due to tectonic forces, gravity, and the pressure from overlying rocks. There's three types of stress: tension, compression, and shear. Strain is how rocks respond to stress and expressed in rocks by folding, which is bending, or faulting, which is breaking. Tension stress causes stretching strain, compression stress causes shortening strain, and shear stress causes twisting laterally strain. Now, the stress and strain can result in many different landforms. You have a thinning crust where you've got rock moving away from each other. You can have folds in the rock layers. You can have horizontal bending that eventually will become a strike slip fault. This folding will eventually become a reverse fault, and this thinning crust can result in a normal fault. Now, if we look at folds on Mount Kidd, Canada, you can see the rocks that at one point were in horizontal layers are now vertically layered. The folded landscape can be seen in many different areas. A lot of times whenever you see cutaways for roads, you can see the different striations of rock that have been folded in different directions. And here's an example of several folds in Utah where you have different rock categories, some being sandstone, some being different types of sandstone, that have been folded in different directions to create landforms. Now, a normal fault is when two land masses are moving away from each other, and you see these faults throughout different areas of the world. A reverse fault is when two areas of land mass or two plates are pushing to each other, creating a reverse fault. And a transform fault is where two large land masses are moving opposite each other. For example, here's a fault where this part of the land mass is moving south and this part of the land mass is moving north. The San Andreas Fault in California is an example of where two plates are touching each other and sliding opposite each other. The North American plate is sliding to the south, and the Pacific plate is sliding to the north. Now, orogenesis is the idea of mountain building or mountain generating. This happens when an oceanic plate collides with the continental plate, or an oceanic plate can collide with another oceanic plate, or a continental plate can collide with another continental plate. And where you have these collisions is where your fault zones are. You're going to have this part of the oceanic plate subducting or going under the continental plate. When oceanic and continental plates collide, which the two come together, the oceanic plate will go underneath because it is more dense than the continental plate. You can also have two oceanic plates converging. Where they converge, they create a subduction zone, and there's volcanoes along the areas near where these converge. You can also have two continental plates that run into each other, and when that happens, you're going to have quite a bit of uplift between the collision area. For example, the Himalayan mountains, which are the highest mountains in the world, are a result of the Indian subcontinent colliding, moving into the Eurasian plate. Now, the major orogenies around the world are the Rocky Mountains in Colorado, the Appalachian Mountains in the eastern United States, the Alps that are in Europe, your Sierra Nevada Mountains in the United States, the Andes in South America, and the Himalayas. Now, along these fault lines and where the tectonic plates collide, that's where the earthquakes and volcanoes are mostly located around the globe. There are approximately 1 million earthquakes every year that can be felt by people somewhere on Earth. An earthquake is when energy is released from two areas of rock sliding across and letting go of the energy all at once. The energy released from an earthquake is called the magnitude of the earthquake, and the intensity of shaking is referred to as ground motion. Now, there's a focus of an earthquake, which is the subsurface area along the fault plane where the motion of seismic waves is initiated. An epicenter is the area of the surface directly above the focus, and you can have aftershocks after the main shock and foreshocks, which are small seismic waves prior to a larger earthquake. So when we look at the earthquake anatomy, you see here's the focus, here's the fault line, you have a hanging wall and a footwall. When these slip against each other, it creates these seismic waves. Directly above the focus is the epicenter on the surface of the earth. Most earthquakes are all going to be down in the ground along the fault line, and the epicenter is directly above it. Now, these seismic waves are measured on a seismograph, and there are several waves that come out of an earthquake. The first one is called a P wave, and it's the fastest wave. And so the P wave is going to be kind of a start, and you'll see this on any of the seismograph papers that are recorded from a seismograph. Your S wave is slower, and then your surface waves that travel along the surface of the earth are your slowest and show up the most. So when you look at a seismograph, this is what an earthquake would look like. Now there's three types of scales to measure earthquakes: a modified Mercalli scale, which measures the intensity of shaking and damage; the Richter scale, which is often reported, which measures the amplitude of the seismic waves; and the moment magnitude scale measures the amount of energy released. So the modified Mercalli scale is when we look at the intensity of the earthquake on what kind of shaking and effects there are on populated areas. So an intensity 1 is not felt. And of course, if there's 1 million earthquakes a year, most of them are intensity 1. They're just picked up by the seismographs. A weak earthquake is intensity 2 to 3. Then you have light to moderate, strong to very strong, severe to violent, and then extreme earthquakes. And then extremely extreme is rated to 12, which is catastrophic, and damage is nearly total. The earthquake magnitude is a quantitative measurement of the magnitude of energy released. The Richter scale is based on the amplitude of seismic waves. When we looked up here, you can see this is the amplitude. So the higher the seismic waves, the higher the amplitude. And that's one way to measure it. But we also use the moment magnitude scale, which is based on the amount of fault slippage, the size of surface area, and the nature of the materials that faulted. And it's a little more accurate for scientists for very large earthquakes than the Richter scale. Now, a tsunami is water that has been impacted by the seismic waves, which creates a very large wave. And many times when you have earthquakes, especially out in the ocean, you're going to have not only the shaking of the earth, but the water moves and actually creates a tsunami, which can be very devastating to people along coastal areas. When we look at the earthquake hazard map in the United States, the largest hazards, or the highest hazard chance of having earthquakes, are along the West Coast. There's also a Missouri Valley fault line here that has a high hazard, and then there's some in the Northeast as well of fault areas that you do have a high hazard. Most of Alaska also is part of that Western Pacific place where the two plates collide, so it also has a large earthquake hazard. Now we can try to forecast earthquakes. A long-term forecast is 10 to 1,000 years. Medium-range predictions are a few years to a few months, and short-range predictions are just a few days or a few hours. We can plan for earthquakes by development of hazard reduction programs. Careful sitting of critical facilities. For example, you wouldn't want to put your big hospital in Los Angeles on top of the San Andreas Fault. Engineering and land use adjustment to earthquake activity. There's a lot of building codes in earthquake rich areas, and development of a warning system. Volcanoes are another result of plate tectonics, where worldwide there's 50 to 60 volcanoes that erupt every year. 2 or 3 of those volcanoes erupt each year in the United States, most of them occurring in Alaska. Japan, Mexico, the Philippines, and Indonesia are particularly vulnerable to volcanic hazards. And there's 3 types of volcanoes: cinder cones, composite, and shield volcanoes. A cinder cone volcano is the simplest type of volcano. It's built from particles and blobs of congealed lava that's ejected from a single vent. Sunset Crater here is an example of a cinder cone volcano that has actually erupted, and that causes this divot in the top. Originally, the volcano would have been like this, and it had a major eruption, but it was one vent, a single cone. Composite volcanoes are some of Earth's grandest mountains, and they rise as much as 8,000 feet above their bases. And some of them that we see are Mount Fuji in Japan, Mount Cotopaxi in Ecuador, Mount Shasta in California, and Mount Hood and Mount St. Helens and Mount Rainier in the Pacific Northwest. The essential feature of composite volcanoes is a conduit system through which magma from a reservoir deep in the earth crust rises to the surface. So you have multiple areas where this magma can reach and erupt in a composite volcano. Shield volcanoes are the third type of volcano and are almost entirely built of fluid lava flows. Flow after flow pours out in all directions from a central summit vent or group of vents, building a broad, gently sloping cone of flat, domical shape with a profile much like that of a warrior's shield. Here's Mauna Loa in Hawaii, and you can see this is formed by the top of the volcano having lava flow after lava flow over time. Now, when one of the composite volcanoes does erupt, it can be quite a violent event. For example, Mount Pinatubo's erupted in the year 1991, and the wind spread the ash westward to almost 42% of the globe. So a lot of air pollution that is naturally created comes from these large eruptions of volcanoes. Scientists monitor volcanoes through many ways: through remote sensing, through checking gases that come from the volcano. They look at taking measurements and ground deformation, and they use seismicity, which is the seismic waves that travel through the earth.